Hi, welcome back for the second part of the video where I'll be focusing on, I think, what was it? Verification scaling. Okay, so let me share my screen. Cool. Let's go here. And yeah, previously we discussed their contributions as to the things that they were doing in this paper, and they introduced this ranking algorithm. And this ranking was basically focused on this uniform Hamiltonian cycle, then choosing top K pivots and comparing the trajectories based on the pivots and the criteria of WI by CI to sort of normalize so that all the pivots are not dominated in the probability mass and the comparison is fair. So in this video, uh, I'm going to be focusing on the verification scaling and discussing the latter part of the um, research paper. So let's go and quickly see what are the things over here and if something, some new information gets added to us. Okay, so equation 3.1 illustrates, so what's 3.1? This thing. Is the reward, right? So this is, I think, the score, but let's see. Equation 3.1 illustrates three independent axes along which verification can be scaled. The granularity of the score tokens G, the number of repeated evaluations K, and the number of evaluation criteria C. Now, each axis targets different source of error in the reward estimate. And we find that the three act as complementary levers. So if we increase the granularity, we improve the score separation between the candidate solution. So let's say if we have more tokens, let's say an integer score from 1 to 20. So if we increase the score granularity, we can distribute the probability mass better. And that can help in differentiating the, what do we call, two candidate solutions much better. The second one is repeated evaluation, which sort of reduces the variance and basically it averages out the biases in individual verification passes. And the third one is the criteria decomposition, which captures complementary aspects of trajectory quality. So what are the different axes in which a particular trajectory is evaluated? So this is the um, criteria decomposition aspect. Now, for all scaling experiments, the authors use Gemini 2.5 Flash as the verifier, and it allows us to extract up to 20 top log probabilities per scoring token. Interesting. In figure 4, we show that verification accuracy on terminal bench 2.0 improves along all three dimensions, rising from 73.1% at G equal to 1 to 77.4% at G equal to 20. I think this was probably this curve. Yeah, figure 4. So as we increase the token granularity to 20 tokens, we see a uniform increase. If not uniform, well, sort of uniform. Um, as the number of repeated evaluations are increased, we see the effect most pronounced during the earlier, like for a smaller number of evaluations, and then we have diminishing returns. And then we also have criteria decomposition as we improve. So we have specification error and output, and then the ensemble is over here. So criteria decomposition is verification accuracy is measured as the pairwise accuracy of the verifier in assigning a higher score to the ground truth successful solution than to fail solutions for the same task on terminal bench V2. Okay, so this is the Bradley-Terry conceptualization, but the decomposition of evaluation criteria, so the specification error and the output. So if we combine all of these, then we have um, an ensemble, and that basically uh, improves the verification accuracy as it's on the y-axis. That's great. Okay, so now let's get back to page 7 it was, if I remember correctly. Yeah. Um, we measure pairwise verification accuracy over 200 randomly sampled trajectories from terminal bench. Oh, very interesting. Spanning multiple agent harnesses. Each axis is a knob that the practitioner can tune depending on the latency budget of the downstream application. Now, while our primary experiments use a log probability accessible model, Appendix B.6 demonstrates that our framework is also compatible with the frontier models that do not expose token level log probabilities via simple two-stage workaround. This is going to be interesting because this is quite useful to if, let's say, a company is trying to implement LLM as a verifier using frontier models. And when log probabilities are not available, then this is quite useful in those cases. And I would love to see like what could be their workaround. In the meantime, if you want to pause this video, you can pause and go to Appendix B.6 to sort of check the, what do we call, um, your idea. So you can think of your idea as to how you would do it with the frontier model and then check B.6 if they do that. So I'm not going to do that in this video, but I think this is also going to be like a one sort of intellectual exercise that maybe we can do later. Also, I just realized some of the things that, okay, so these are the things that I need to do today. So this is for my own work, but let's say I'll create a YouTube tab over here and add checkpoints plus links in the video, learn how to do it, and implement this in future videos. Or if this exists, or if this could be applied to pre-existing videos on the channel. So this is interesting. This is something that I need to do. And okay, I'll talk about and okay, statistical tests video for what was the video? Responsible evaluation of AI for mental health. Okay, so these are the tasks that I need to do. Sorry, I just had to make notes. Okay, so we can talk about this basically like they describe how you can use the log probabilities in section in appendix 3.6. Now, this is the most important thing. We have to understand what are these three things, which is like the three scaling axes. The first one is the token granularity, the second one is the repeated evaluation, and the third one is the complexity decomposition. So the first one is scoring token granularity. Now, standard language model judges collapse the scoring distribution to a single highest probability token, yielding a discrete reward RLM T given tau, uh, which is sample which is part of 1 to G, where G is basically let's say an integer from 1 to 20 with the resolution of 1 by G. Intuitively, enlarging the ordered token set V score does not grant Intuitively, enlarging the ordered token set V score, which is basically this from 1 to G, does not grant the verifier any new information about the trajectory. Yet it grants the decoder a finer space in which to project the model's internal belief. Yes, that is exactly what we discussed. So that nearby beliefs that would have been rounded to the same integer are now mapped to continuous rewards. So signal to noise ratio to isolate why finer granularity improves verification. We decompose pairwise score gap delta is equals to SC minus SI between the correct SC and incorrect SI trajectories into signal and noise component. We define the signal to noise ratio as in equation 4.1, table 1 on the left. So this is basically what they do is the expectation of the correct score minus the incorrect score, uh, and uh, basically defined by the standard deviation, um, normalized by the standard deviation. Where ESIC captures how strongly the verifier prefers the correct trajectory over the incorrect one, which is the signal strength. SNRG E S of C minus S of I variance of S of C. Okay, granularity increases. I think this is for the terminal bench task, or like what's SNR? Oh, it's the signal to noise ratio. So as we increase the tokens, the signal to noise ratio increases. Interesting. The SNR measures how reliably the verifier separates correct SC from incorrect SI trajectories. As the number of scoring token G increases, the SNR grows, indicating better calibrated score separation. And it's converging to 20. Interesting. Um, so, and the variance dominator var SC minus SI captures how inconsistent the preferences across pairs, which is the noise. So pairwise verification accuracy is a monotonic function of SNRG holding a sample size fixed. A large standardized gap implies a higher probability that SC is greater than SI. Empirically, we find that SNRG increases from 0.775 at G equal to 1 to 0.799 at G equal to 20 on terminal bench. Finer grained tokens therefore produce better calibrated scores that more reliably separate correct and incorrect trajectories, which in turn improves the pairwise accuracy from 73.1% to 77.5%. Interesting. Let's see a case study to understand it better because this is more theoretical. A lot of this information might does not always make sense because they still haven't exactly described what it is. Case study. So if we want to optimize a query, right, to concretely illustrate how scaling granularity to G equal to 20 and our probabilistic formulation sharpen the verifier signal, we analyze a representative trajectory pair from the query optimization task on terminal bench V2. This is generated by Claude Opus 4.5 under the Open Hands harness and scored by Gemini 2.5 Flash. Here, the agent is given a slow SQL query over a database and asked to produce an equivalent optimized version. Both candidate trajectories generate queries that execute faster, but they differ critically in their verification processes. The correct trajectory waits the full 5 minutes to the original query for the original query to complete on the canonical database and performs a direct diff against the optimized output. In contrast, the failing trajectory never validates equivalence on the database and instead creates a new database, as shown in the reasoning traces in Appendix P.4. Gemini 2.5 Flash reliably identifies this failure mode but expresses it in graded, hitched language, example, slightly cleaner, marginally more direct, as if the discrepancy were minor. When evaluated over 100 repetitions, a standard language model judge on a scale of 1 to 5 collapses these nuanced assessments into discrete scores. So this is defined in table 2. Producing ties, example, 5 versus 5 in 88 out of 100 runs. Yeah, this is crazy. Thus, failing to meaningfully discriminate between the candidates. Taking the expectation over the same 5-point distribution eliminates ties entirely, ranking the correct trajectory higher in 69 turns. This is a big improvement. And the scaling granularity to G equal to 20 sharpens the signal further, letting the LLM as a verifier rank the correct trajectory strictly higher in 77 out of 100 turns. Yeah, so what we can interpret from this is, and I will also go to Appendix P.4 because that is where most of the crux lies, most of the content and the juice and the nuance lies. But the TLDR, if I were to interpret this, I would say that taking the expectation over the same 5-point distribution. Now, this is the critical highlighting point. So, in this document, if you guys remember, I was taking expectation over from 1 to 20. So, if we have a 5-point scale, then we can take an expectation or the probability over this particular um, over these token sets. So I think this is the main idea which I initially captured, but let's go to B.4 and understand the case study. So the task instruction is that you are an open English WordNet database and I implement a SQL query, but it's not optimized. So this is basically the main idea. Please save your solution in this. Please make a query as efficient as possible while ensuring the same output is produced. So this is another evaluation criteria while ensuring the same output is produced. Um, Finally, please use SQLite syntax. Now this is also another request. Um, Now this is also important. Now, ground truth breakdown. Both candidate trajectories have optimized SQL query and report a passing internal diff check, but terminal bench's hidden grader assigns reward 1 to one and reward 0 to other. The failing trajectory verification step is methodically unsound. And why is it methodically unsound? The agent attempts to run the original query twice, 60-second timeout, then 5 minutes, and aborts both times. To So this is original query, which is the unoptimized version. To obtain a reference output, the agent runs this and then issues create index on census. Okay. Subsequent steps compare original query on indexed copy to optimize query on canonical unindexed database. Two different physical access paths whose tied order by keys are not guaranteed to break the same way at the limit 500 boundary. All verification artifacts are then deleted, removing any evidence that could be rechecked. The optimized query is therefore never actually validated against the original on the canonical unindexed database that the terminal bench grader uses. Skylight fails. So Gemini 2.5 reasoning trace. Across 16 reasoning traces, with thinking enabled, the verifier reliably identifies the soundness issue. So this is an excerpt. Unable to execute the original query by completion on the provided app Uven.SQLite database with a reasonable time frame. It was interrupted twice, once after 60 seconds, another after 5 minutes and 2 seconds. To obtain reference output for comparison, the agent copied the database and then added indexes to this copied database. By modifying the database to obtain the reference output, the agent violated the implicit constraint of the task. So this is the reasoning that it gave, and it makes sense. Therefore, it does not correctly verify that its optimized query produces the same output as the original query running on the original unindexed database. So this is the second one, but I think we get sort of like the gist as to what we were doing. Are basically trying to compute the distribution over the scoring tokens that we are that we want. And once we have that distribution, basically the same 5-point distribution as mentioned over here, we can use the log probabilities and the formula and the formulation over there to make sense of the granularity and how we distribute the probability mass. Now, judges versus verifiers on query optimize. Over 100 repeated evaluations, we count how often the correct trajectory is scored higher than SC greater than SI tied with SC equal to SI or lower than SC less than SI, the incorrect one. Okay. The discrete 1 to 5 judge produces ties in 88 out of 100 evaluations. Taking the expectation over the same 1 to 5 scale eliminates C, taking the expectation over the same 1 to 5 scale. So this is exactly what our interpretation is. So eliminates ties and correctly ranks the trajectory in 69 out of 100 evaluations, increasing the score granularity to G equal to 20, further improves discrimination. Um, correctly ranking the trajectories in 77 out of 100 evaluations. Yeah, so as we increase the s- number of scoring tokens that we have, then we have better, um, we improve the evaluation. To by scale, increasing the score granularity to G equal to 20 further improves discrimination. What I'm going to do is, just for the sake of clarity, I think creating a new video out of this might not be the most ideal or the most optimized way. Um, Granularity here isn't the task. By increasing score granularity, what do we mean? And I think this should be done for this. So let's ask AI. That's why I love AlphaGive. Um, I didn't do it for the statistical tests thing because it would, I think I did do it over there, but I was not able to understand it better. Let's see if we can have some better interpretation over here. Oh, wait, whoa, whoa, what happened, brother? Come on, come on, come on, come on, come on, come on. Please don't do this to me. Okay, so my notes should have been saved, right? Whoa. I just said I love AlphaGive. Yeah, this is breaking my heart. I don't like this. I don't like this at all. Huh, never mind. If we have a setback, we'll move on. We'll learn to live with it. Okay. Actually mean. Please, 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 come on, buddy. Ugh, I don't like this. I don't like this one bit. Let's see. In the context of LLM as a verifier, okay, so there's a lot of information I need to parse. In the case of LLM as a verifier, the score granularity does not refer to the range. Okay, so I was incorrect over there, but rather the number of tokens from the model's probability distribution used to calculate a continuous score. Number of tokens. So let's say if, hmm, does it mean that we can do like a chain of thought? If we ask the model to do a chain of thought and then give the score, is it the same thing? The LM judge simply outputs a single most likely token. This framework treats the model's internal logic as a probability distribution and calculates a mathematical expectation of the score. In typical LMS judge setup, if the model is asked to rate a solution from 1 to 5, it might assign probability 0.6 to 4 and 0.54 to 5. A standard judge would simply output 4. LLM verifier uses granularity parameter to determine how many of these potential tokens to factor into a final continuous value. So the continuous reward R is calculated as expectation over the top G score tokens. Extracted the probability of the model assigned to a specific token score, the scalar value of that token, the number. By increasing granularity helps. By increasing G, the system captures more of the model's internal uncertainty or hedging. Okay, at G equal to 1, the verifier acts as a standard judge, picking the most likely integer. At G equal to 20, verifier looks at the probabilities of all the numbers in its output vocabulary. It's doing the same thing. Even if two trajectories both have 5 as their most likely token, one might have 4 as its second most likely token, while the other has 3. The expectation calculation will distinguish these two, given the first giving the first a higher continuous. Case study breaking does. Okay. Illustrates the query of 1 to 5 just produces 88% of the ties in 88% of the evaluations, but using continuous formulation and scaling granularity to G equal to 20, they eliminate ties. Okay. Okay. Give me an example of how this granularity increase actually look like for the task. Is it like, okay, I'm not going to bias it. Let's just see what it comes up with. Got it back. I got it back. I got it back. Awesome. Okay, so what we have here is in the context of this paper, score granularity G refers to the number of discrete levels on the rating scale used to evaluate. See, what the hell? Okay, while many systems use simple binary check, discrete and continuous scoring. Okay, okay, makes sense. Yeah, so I think this formulation that we have is correct. The formulation that we had over here, it is actually correct. Yeah. Because like it does not really make sense any other way. This is the only reason, the only way it makes sense. Yeah, we calculate the expectation. Yeah, just checking. Yeah, let's see what it comes up with. It sees its confusion now. So maybe over here we have a better answer. Oh, interesting. Yeah, so see here. It's probably mentioned in the somewhere in the appendix. It's the levels, it's the classes. So we were right all along. Okay, sorry for the detour, but it was needed for me to make sense of what I'm saying. All right, so verifier continuous, judge is discrete. Now, when we talk about the repeated evaluation, right? While granularity improves the score calibration within a single forward pass, it does not address a second source of error, which is the verifier's variance on just one evaluation. And this is really important because a lot of the times LLM as a judge, and even I have made this mistake, and even I'm still making this mistake, um, which is to just do one pass of evaluation and be like, oh, okay, I have got the results. That's not ideal. That's not how good research is. So we need to reduce the variance. Um, Okay, what I'm gonna do, I'm gonna just stand now. I'm so tired sitting down. It's slowly gonna come up. All right. Wow. Awesome. Okay, so averaging K independent evaluations one by K Monte Carlo is a Monte Carlo estimator of the underlying expected order. Variance shrinks by one by K factor, of course, makes sense, while its bias is unchanged. Yes, true. This is important. Bias is unchanged. This complements granularity rather than duplicating it. Granularity sharpens each individual estimator while repeated evaluation averages out the noise and granularity cannot remove. Um, figure for the middle part shows that the accuracy increases from 74.7% at k equal to 1 to 77.5% at k equal to 16. However, the gains diminish with larger k, and this is what I mentioned earlier as well. Now, early improvements rise from the variance reduction. So that's the main idea. Um, while additional evaluations contribute diminishing returns due to correlated biases on harder samples. Correlated biases. What are correlated biases? Let's ask. Okay, so it's going to draft our answers. So, but more importantly, repeated evaluation refers to, I lost it. A wider range scale combined with extracting. That's okay. I'm not gonna use Pro. I'm gonna use cost effective, cheaper versions. Um, a 1 to 20 scale gives the model more bins to put its thought. No, this is not what I want. Where are the correlated biases, brother? Yeah, I don't see it. Maybe I will see it now. No, let's leave it. I'll get flustered if I think more on this. But the main idea is that I was on this repeated evaluation. While increasing K helps break these ties through averaging, this mechanism is fundamentally limited to discrete judges. We show that a single pass verifier K equal to 1 already matches a heavily ensemble judge where K equal to 16, highlighting that fine-grained probabilistic scoring provides a stronger signal. Makes sense. Um, okay, what happened? Come on, bring me. Oh, yeah, I got everything back. All right. All righty, all righty, all righty. All right. Now let's talk about criteria decomposition. Now, granularity and repeated evaluation both assume that the rubric itself is adequate. Neither helps if single monolithic criterion is poor proxy for trajectory quality. Makes sense because if we just evaluate everything in one prompt, not ideal. In long horizon agentic tasks, judgment like is this trajectory correct basically conflates several logically distinct factors, and verifiers asked a compound question, which often latch on to whichever factor is most salient in the prompt. And that is very subjective. It's very dynamic and introduces consistency issues. In the previous paper that I discussed, one of the things that was super important was how do we replicate evaluation in a reliable way, which if we do the test again, it makes sense a lot of the times because there's sampling, but also the models are initialized on different even if the weights are same, but there can be floating point errors during inference, and all these errors compound, which can lead to different interpretations of the same prompt. Although with stronger models, it's a much lesser of a probability, but it still exists as one can imagine. Now, if you have like one big prompt, one big monolithic prompt, it might not a model might miss out on certain things if and only if the model is not no okay, so a bigger model can also make the mistakes, but smaller models do miss out on bigger context information, and this is um, often observed across every single model type. So therefore, what's happening over here is that instead of putting the evaluation entirely on this one single trajectory, we replace a single monolithic rubric with an ensemble over C simple subcriteria. Now, concretely for code agent trajectories, we decompose correctness into three factors, which is specification, the errors, which over here, which is the output. Yeah, I'm tired. Output and also the errors. So this was the initial image that we saw where we have specification, out errors and outputs. So basically, if you have a bigger prompt, decompose it into simpler individual tasks that is much easier to evaluate, and the scores do not conflate and go to any of the other things. Now, experiments. We evaluate LM as a verifier as a trajectory reward model for test time scaling across four benchmarks that span three domains. First is coding, the second is SWE bench, and third speed SWE bench verified. We have robotics and we have medical. Across all four, we use the same protocol. A generation policy pi theta produces n candidate trajectories per task, and the verifier scores every pair uses using the probabilistic pivot tournament as described in algorithm 1, and the trajectory with the highest normalized score is submitted. Unless otherwise noted, the verifier is run with with the granularity g equal to 20, which is repeated over 8 times, and and we have three criterion decompositions that take place. The results were reported as such, where we per benchmark performance and gains from verification. Baseline accuracies are on the left, and um, so this is the baseline accuracy of different models, as we can see over here. Um, so on terminal bench, pass it one, which is an Oracle, and LLM As A Verifier. LLM As A Verifier is doing really good work over there. Um, so they basically report performance gains over SWE bench. They measured 4.5, G3, and 2.5. Or Meridian bench they also do the same thing. Baseline accuracy. Oracle, our method consistently improves pass at one and recovers large portion of the Oracle headroom, achieving state of the art. So see even Oracle at 75 and they got to at 73.3. But the improvement is not super great when compared to pass at one for So they have 76.8%. They have 78.2, 75.8, 75. Improvement is there, but like, okay, so these are the baseline model accuracies in this. And if we use these models, oh, but they use Gemini 2.5 Flash, right? If I remember correctly. Yeah. Um, I think it was mentioned much earlier somewhere. For all their experiments, they use Gemini 2.5. Yeah, see Gemini 2.5. Yeah, my memory is correct. Is very correct. Okay, so Terminal Bench V2 measures agent proficiency in shell-based environments across long horizon tasks, require multi-step reasoning, file manipulation, recovery from the failed tool calls. We use CAPI, and this is their experiment design. And what if, okay, so they have basically like different settings on how we further show the gains are not tied to specific hardness. So this is important for additional generalized. So like if you build agentic systems and if you're going to use agentic systems for inferences, they're trying, I'm not sure what harnesses are. I'm assuming these are scaffolds to effectively run agents, and these are different libraries to do that. And I think they did ablation experiments regarding specific harnesses so that the gains are not specific to a particular hardness. So I think that is important for the result as well. Now, SWE-bench verified. SWE-bench verified is a human curated subset of 500 real-world GitHub issues, where each task requires an agent to produce a patch that resolves the issue and passes the maintainer's hidden test suite. It stresses long context reasoning, cross-file edits, and compliance with an existing code base, and we use mini SWE agent as a scaffold. Um, okay, so we are getting some. Ah, mini Sweden scaffold. This is cool, cool stuff right here. Um, the mean pass candidate pool is 76.1, and the Oracle pass at 3. And the Oracle pass at 3 upper bound is 84.4. LLM As A Verifier, she's 78.2, and the at pass at 1. Do they do pass at 3? Oh, this is a candidate pool. Okay. I'm going to sue them. Yeah, I'm just exhausted with it. Yeah. Okay. Never mind. It's life. Happens. Okay, so we have robo reward bench, reward models on on r robotic manipulation trajectories. We curate pairs of rollout videos that follow the same natural language instruction but make different amounts of progress. The reward model must output a preference indicating which rollout makes more progress. Unlike the coding and clinical benchmarks, inputs here are multi-frame videos. So the verifier must integrate visual context across frames to reason about physical progress towards the goal. Makes sense. The modality is different. We use Quen 3.6 35B as a base VLM verifier and apply the same probabilistic formulation over scoring tokens extracted from the VLM's logits. With granularity g equal to 20 and k equal to 8, blah, 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 blah. Okay, so basically individual, and with that, they were able to reduce the mean absolute error on this. MAE, as you can see over here. I don't want to do anything, sorry. I didn't do anything. I did not do anything. Okay. We report mean absolute error, MA lower the better, of course, between human labels and the predicted labels, and they were able to do decent stuff here. We observe strong correlation between the chronological progression of code generation steps and the scores from LLM as a verifier. So normalized step is doing much better, and ideally, which is the success trajectory was like this, and error compilation was over here. So normalized verifier score was going up. Okay. The example task above requires the agent to run MNIST inference. The successful trajectory follows a coherent sequence of events which where we read the model, we install CPU only torch, and we update hidden dimensions and exhibit consistent and this exhibits consistently increasing verifier scores. And in contrast, the failed trajectory is characterized by erroneous behaviors and it unnecessarily installs a large torch vision package. So there's optimization definitely over here, and I think it's also part of something that the SWE bench covers. Okay, so we have the med agent bench where LM agents on medical tasks that involve patient information retrieval, guideline lookup, multi-step tool use, and in simulated health records environments. Oh, okay, interesting. It covers a regime where ground truth trajectory checkers are expensive to construct and where verification errors carry real safety consequences, making it a natural stress test for general purpose verifiers. We use the agent bench harness and sample n equal to 5 trajectories per task from Claude Opus 4.8 and then apply the same verification procedure. Okay, makes sense on so the pass at Cloud Opus 4.8 on the spool is 70.2%. What's the oracle? Is there an oracle given for this one? Is it? Hmm, never mind. So let's talk about fine-grained verify signals as proxy for task progresses. Okay, so now this is for more like reinforcement learning, where we can sort of, okay, so this is quite interesting. I want to understand what this task progress is before commenting. So let's dive right into it. Now, beyond selecting the best trajectory, the fine-grained signal produced by LM as a verifier can serve as a scalar proxy for how far an agent has progressed through the task. Now, we quantify this using value order correlation, VOC. So the Spearman rank correlation between the chronological index of the step and the verifier's predicted value for the prefix ending at that step. Following Ma and all, so what's this paper? Terminus 2. Okay. Intuitively, a verifier that tracks task progress should assign monotonically higher scores to later prefixes of a successful rollout, yielding VOC approaching 1, and should remain robust to failure modes such as getting stuck or should not regress. Now VOC on code generation on terminal bench V2, we measure VOC between the chronological step of each agent action and the verified score on the corresponding trajectory prefix. So we're trying to find some correlation between the agent steps and the corresponding and the verifier score on that. So if the verifier score is high, if it is passed, how many steps does it take? If it takes a more number of steps, then this can serve as a positive correlation. So let's look at this. LMS verifier produces consistently increasing scores on successful rollouts while remaining largely flat on trajectories that stall or drift toward failures, allowing allowing the same scalar to serve as both a progress measure and an early warning signal. So this is really good for um, building process reward models as well, because let's say if you flag certain rollout, you can stop the generation there and save inference and then maybe try a different strategy or maybe just focus on other rollouts. So this can also save inference compute and help distribute inference better. Um, this tool this tool uses this tool use motivates our Claude code and codex extensions. Okay. Anti Spearman VOC was a verifier. That fine-grained signal produced by LLM as a verifier is not merely a better ranked, but a calibrated estimator of task progress. Okay, now VOC on robotics. We compute VOC over 500 trajectories from held out robo reward dataset as shown in this qualitatively almost TOPR reward tends to saturate people almost immediately. Calm down. It's okay. Things happen. It's life. We'll get through this. TOPR reward, qualitative TOPR rewards tends to saturate people almost immediately and therefore lose its ability to discriminate mid-trajectory progress when a rollout eventually fails, whereas our expectation over the full scoring distribution preserves a smooth, chronological aligned signal throughout the episode. All right. I can learn to live with this. I can probably make sense of it. Uh, Dense reward for reinforcement learning makes sense. This is training steps. Oh, so they used it for dense reward. They used like dense reward for reinforcement learning as well. Um, Now to give you now, I know I am sort of jumping across multiple things like really quickly because these are more experiments and how they did it. Um, to understand like how you could formulate dense reward for reinforcement learning, you are having a rollout. And just in the previous section, we discussed how we can verify certain trajectories, certain because there was certain correlation. So if we use LM as a verifier uh, at certain steps along the way, so those steps can be used to at least benchmark, not benchmark, but assign score to certain parts of the uh, rollout that we have. And that score can be a dense reward for reinforcement learning and not sparse rewards like for which happens with outcome-based reward models. So we can sort of have, if not process reward, we can have like a process reward models where we um, are not assigning score to every token, but parts of trajectories, which is like super important. So this can be used right over here. The process signal from the previous section also helps to remediate long-standing difficulty in reinforcement learning, the credit assignment problem. And we show that the fine-grained score of LM as a verifier equation 3.1 is a drop in dense reward for both off-policy and on-policy reinforcement learning and improve sample efficiency without any reward model training or environment-specific shaping. Very important. So if you're using LM as a judge, even for offline reinforcement learning, we use LM as a verifier, much better. Now, off policy reinforcement learning dense progress rewards for DSRL SAC. Um, with soft actor critic. At the end of each rollout, we query VLM verified with the task construction X and the an uniform subsampled sequence of rendered frames. Uh, so task construction X per step progress curves. We then relabel the rollout with the shaped reward. On policy is like reinforcement learning. So we have correctness, format, and reasoning. During early stages of the training, it is common for all sample responses to produce incorrect final answers, causing the group relative advantage to collapse to zero, yielding no gradient. And LLM as a verifier mitigates this issue by evaluating the reasoning trace of each completion using the probabilistic pivot tournament, assigning each response a normalized preference score, and then that captures fine-grained differences in reasoning quality even when the final answers are identical. Huh. But we are still using an external judge, LM as a judge. There's still LM as a verifier in the loop. We can do the same thing with LM as a judge on that. Yeah, this is dodgy. This is dodgy at best. Yeah, I don't like it. During the early stages of the training is common for raising trace of each completion using the probabilistic pivot tournament, assigning each response normalized reference score that captures fine-grained differences in reasoning quality, even when the final answers are identical. So, are we using LLM as a judge? Are we really doing that? We're trying to compute. Okay, so if we're not using a criterion per se, we can use intrinsic probabilities to come up with something, but again, we would not have the final score because if we multiply it by the final score, the reward is essentially zero. So we do not multiply with the final score. So what do we do? Okay, so instead of 0, 1, you're assigning a different reward for each trajectory. That's it. So you basically speed up the training somewhat. But I think with GRP, if I remember correctly, it didn't show a lot of improvement when they compare it against GRP, right? Yeah, I think they mentioned something with GRPO, but I think it did not show a lot of improvement with GRPO. Okay, so this is the number of steps. It's still better because you can see earlier, but then it sort of converges success rate. So yeah, it converges. Makes sense. Makes sense, buddy. Makes very much sense. In this work, we argue that verification constitutes an underexplored axis of scaling. To realize this, we propose LLM as a verifier general purpose framework that delivers fine-grained feedback for agentic tasks, unlike standard language models judges that output single discrete score. Our approach computes a continuous reward by taking the expectation over the distribution of scoring token lodges and enables verification scaling across multiple dimensions, including score granularity, repeated evaluation, and criteria decomposition. Now, when used as a trajectory reward model for the test time scaling, it achieves state-of-the-art performance on terminal bench V2, C bench, verify robo bench, robo reward bench, and mediation bench beyond ranking and blah 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 blah, improving sample efficiency and GRP on robotics and mathematical reasoning benchmarks. Test time scaling, self consistency, and all that stuff would come over here. Decomposing problems into simpler sub problems, marginalizing inference aware training, parallel self verification, general reasoning, repeated sampling, latent. Oh, what's latent world states? Reasoning with language model is planning with word model. Huh. So AI for health. I would love to look into this. Want to read? Let's go. Let's go. Let's go. Let's go. Verifiable reward. Reward models convert candidate solutions, actions, or trajectories into scalar feedback, selection, monitoring. Okay. Yeah. Thank you. A very long paper. Tired. I too am very tired. But yeah, I think the overall idea is that LM as a verifier, instead of discrete output, asking LM to choose an option 1, 2, 3, 4, 5, you take the distribution over the discrete space so that you get continuous outputs, and then you reduce biases, and then you reduce, um, and you also like do the repetitions, um, basically the repeated sampling, and you also break the problem down into um, less complex structure so that the model is able to understand and score things effectively. One thing that I'm sort of curious about is how this would scale for if all of these factors had not been done. If all of the let's say if we do not do the bias, like if we do not do the repeated experiments, um, what would happen? I want to understand what if we do not do repeated sampling, or we do not do the granularity scoring. Do the authors mention the reasons of why these are important? This is, I think, the question that we should be asking. Dedication of the paper explaining exactly. Yeah. Okay. Yeah, this felt like an attack to me. It's standard element believe into a single integer. Yeah, I do know that. I do know that. Okay, so I lost the final answer. So I'm assuming they are not showing n min the last answer, the nth answer. So they're showing only showing n minus one. So I just did this to get them riled up. Now I will have my answer. Okay. Yeah, I knew this. Thank you so much for your support. All right, that was it for the video. It's been a long video. Great paper. I have added a link to this. Let me know your thoughts, and if I got something, if I missed something, or if I misinterpreted something. I tried my best. I'm still learning. So let's see. Thank you.